Um, First, we're going to start with our keynote talk by Professor Wayne Schubert. I think at this time, everybody should know him already, so I'm going to give a very brief introduction. Professor Wayne Schubert got his bachelor, master, and PhD all from UCLA, and we all know he got PhD with Professor Arakawa in 1979. And since then, he 73, yeah. Sorry. And since then, he had been a professor at Colorado State University before he retired. And he had made so many accomplishments, and during his career, increased the George Charlie Medal in 2016. I want to mention particularly one event was honored to him at the AMS Centennial Annual Meeting. I want to just quickly cite the citation for him, and mostly for his contribution have been so far-reaching and pioneering and yielding profound new insight into tropical cyclone, moist convection, and the dynamic mesoscale and synaptic scale phenomenon. Without further ado, I'm going to pass the mic to Professor.
Can you put it on full screen?
Oh, sure.
Yeah. Thanks. Yeah. Thank you. Well, thanks very much for attending this. I have some reflections on Arakawa's views over the years, and I prepared this in collaboration with Rick Taft of the Atmospheric Science Department. He provided a lot of insight to me on this. So I wanted to talk a little bit about...
Could you say a little who Rick is?
Rick is a research associate in our department, and he has worked there in our department for 30 years or so. And he appears as a co-author on a myriad of papers. And he's very happy to be in the background, but his contributions are just amazing. He has a degree in math, not in meteorology, but he knows a lot of meteorology by now. So I'd like to say something about Arakawa. He was born in July 1927. Fukui, Japan. And Fukui is pretty much straight west of Tokyo. And right there. And actually, I have a circle around it, I think, there. And I'm told it's 100,000 to 200,000. It's not a huge city. So he was in high school in the early to mid 1940s. He was born in 1927. So at 18 to 27, you get 45. So he was 18 years old when the war ended. I think he was lucky. He could have been killed, you know, if he would have been drafted, you know, a couple of years earlier or something. But he says, at high school, I was interested in science in general. There was no question about my future. And he says, I was not drafted. I was 18 or something like that. But I had to go to the factory. He had to work in the factory a bit when he was in high school. And he had to go to both fire stations. My understanding is he had to report about every 3 days or so to the fire station. And you know what this is. This is fighting incendiary bombs, the result of incendiary bombs. He said he didn't like to talk about this. I could really tell he didn't like to talk about this. But he did say, that's quite an experience. When there is an air raid, of course, it is completely dark. They run the fire engines. They had to, and it is very dangerous. Sometimes the fires are so bad or so high, firemen cannot do anything. Once we were trapped by fire. So I think he was lucky to get through that. So after the war ended, he entered Tokyo University and he studied physics. He graduated in 1950, and I think he's almost engaged at this time. And here's a great picture of him with Kazuko, who I hope some of you met last night. And so he graduates in physics, and the way he says, there's no jobs available in physics. And so there were jobs available in meteorology at JMA, the Japanese Meteorological Agency. And so he applied for one of these jobs, and he got it. And this is an interesting quote. I entered the Japanese Meteorological Agency after I graduated from the University of Tokyo in physics, so I didn't go to graduate school, and I didn't take any course in meteorology in my whole life. Can you believe that? So, and then he said this, JMA administrators must have recognized that my real interest might not be in meteorology, so they put me on a weather ship. Another victim of this policy was Vic Uyama. At least in my case, the policy worked. I didn't know what he meant by that. But so I thought about it for a long time, and I think he means that after that experience, Arakawa stayed an employee of JMA, but Uyama didn't. And Uyama went to graduate school at New York University. So I have a map here of the two weather ships. And when I first heard this story, I thought, oh, they sent you on a weather ship for a year. That's not right, because a weather ship could only stay on station for 21 days. So they had 6 ships, and they rotated them between these two stations. And I think he was on 6 or 7 deployments. So like 6 or 7 months, he was out at sea on this weather station. And this station, he said, was called X-ray. And he said the weather was especially tough at the northern site in the winter when cold air flows out from the continent to the warmer ocean. During such an event, air becomes moist convectively unstable in the lower part. It's warmed and moistened by the sea surface. Because the air above the boundary layer is relatively dry still because it's flowed off the continent, the resulting cumulus convection is usually not associated with a lot of anvils. So he could see the clear sky between cumulus towers. And I think he maintained this picture. He used to watch this from the weather ship. And 20 years after that, he made this schematic diagram. And I think that must have been what he saw from that weather ship. He saw the Ith cloud. And I think at this time he thought, okay, the clouds come in ensembles, and they're different heights. And so if you're going to model this, you have to have a spectrum of clouds with different heights. Some of them penetrate this surface. Some of them just reach that and detrain at that level. So I think he had a love for baseball. I think JMA must have had a baseball team, and so there he is there. So he was in JMA for 10 years, all through the 50s, and in particular was at MRI, the Meteorological Research Institute. And at this time, he's learning meteorology on his own. He's reading these classic papers from the Institute for Advanced Study. And in 1956, he told me he read the paper by Phillips on the general circulation model. He just thought that was amazing. And nobody in Japan, he said, was really thinking about the general circulation. So he thought he should write a monograph about this. And he did this in 1958. And I understand this is famous in Japan, but unfortunately, I don't think it's ever been translated, so English speakers don't appreciate this, I believe. So during this time, JMA had no computer. So 1959, they decided to start operational numerical weather prediction. And Arakawa says they have two possible computers. One is a UNIVAC and one is an IBM. And these people, they're just thinking about Fortran, but I think they don't understand how to use Fortran or anything. And UNIVAC is not developing Fortran compiler or anything, but IBM is. So they buy an IBM machine, and I think Arakawa learns to operate it, actually. Because when he comes to UCLA, he told me he operated the computer here at UCLA. Anyway, Japan is the third country in the world to start operational NWP. US is first, Sweden is second, Japan is third. So in 1960, there's this international symposium on numerical weather prediction, and Japan attracts all these scientists from all over the world, including Charney and Fjortoff and Phillips and Yale Mintz. And so they all meet these Western scientists, and Arakawa meets Mintz, and this, we think this picture is taken in 1960. And so Mintz invites Arakawa to come to UCLA, and he comes for a 2-year visit. And there's a whole situation with a visa. I think he can't come for longer than that. It's a J visa. So he comes, and during this period, he derives the Arakawa Jacobian. So this is how he does it. He says JMA gets this computer, and they were making barotropic forecasts, and Arakawa is looking at the output every day, studying it carefully. And he sees things like this. The solid lines are contour lines, geopotential contours, and the shaded region is vorticity. And he says, I didn't do this. My colleagues put the vorticity contours on there. And he says, this is a really fortunate thing, because I wouldn't have discovered the Arakawa Jacobian if they didn't put the vorticity contours on there. So I was wondering, well, here's what he said. And this is the way he explained it to us students. I watched and examined vorticity fields predicted by the model every day. Noodling, and it took us a long time to understand what he was talking about with noodling. That's a term that's not used anymore, really. It's usually called filamentation now. So he said, I observed noodling of the vorticity field. So he had to have the vorticity field on there to see noodling, which is what you see over here in red. And he saw this on predicted maps. And he said that model would blow up sometimes within 48 hours because of noodling. And then he would tell us, well, there's two kinds of noodling. There's real noodling and there's false noodling. And he said it's a false noodling that caused the problems. So how do you tell the difference between true noodling and false noodling? Well, let me show you a numerical integration that's made of the barotropic model, non-divergent barotropic model, using the Arakawa Jacobian. And in his paper, he has both a second order and a fourth order Jacobian. So the results I'm going to show are for a fourth order Jacobian, so it's more accurate. And what it is it's a ring of vorticity that you might get, say, in the eye wall of a hurricane. So the eye of the hurricane, you're not generating so much vorticity, but in the eye wall convection, you're generating a lot of vorticity. So you get this ring of vorticity. And if the ring is narrow enough, it goes unstable barotropically. And the way you can think of it is it's a ring of high vorticity. So as you go radially out, the vorticity jumps up at this edge and it jumps down at that edge. So the Rossby waves can propagate along there in opposite directions, and they can phase lock, and it goes unstable. But the ring has to be thin enough. So watch this integration, and I think you will see true noodling. But I'm not sure about this, whether there's false noodling in there, because Arakawa's Jacobian does not eliminate false noodling. It controls it. And he made this very clear. He said you can eliminate aliasing error with spectral models if you use the transform method, but in his finite difference, you cannot eliminate aliasing. You can control it. So here's the integration. The time is running there at the top. The vorticity field is shaded, so the red is high vorticity. The scale is right here. You can see it's going unstable at wave number 4. And some of the low vorticity blue in the eye is coming out into the eye wall. So the eye is actually getting smaller through this asymmetric process. And now it noodles. I think that's true noodling.
Not entirely.
Not entirely, yeah. Probably not entirely, yeah.
Wait, according to Webster's, noodling means catching a catfish with one's bare hands.
Catching a catfish with what?
One's bare hands.
With one's bare hands.
So just so you know.
Arakawa told me it was Japanese noodles. I looked it up once, and there's all different kinds of Japanese noodles, so I don't know which one he had in mind. So anyway, that is his Jacobian. So he had to go back to Japan after he discovered the Jacobian there. And during that time, this is interesting, during that 2-year interval, general circulation modeling started at UCLA. Do you know how many people were involved in it? 2. Arakawa and Mintz. And they got to use the computer up at the business school. And they got to use it on weekends, I think. And I think Arakawa had to operate it, because they didn't have any operator on weekends. So he had to go back to Japan for 2 years, and then he came back to UCLA in '65, and he was offered a faculty position here. And I didn't know this, but he wasn't sure whether he should accept this. And he wasn't confident about 2 things. One was his English, and I think my guess is that his older brother spoke really good English, and he always compared his English to his older brother's English. So he wasn't confident about that. And all the time he worked for JMA, I don't think he ever taught anything. So he's going to come to a place where he has to teach, which he's never done. He has to teach in English. He almost turned it down, I think. Boy, that would have changed things if he would have turned that down. So here is some pictures of him. And this picture on the right here, when I saw this, I thought, he's not going to like this. You know why? Look how messy his office is. And so when he came back, the program blossomed, and he started taking on all these students, including Dave. And Dave and I got to go to Boulder with him for this. It was kind of a pre-gate workshop thing. I asked Dave the other day, what is that in our pockets there? Arakawa doesn't have one. Is it some kind of a name tag or something? And Dave says, no, that's the Continental Airlines ticket. I don't know why we carried that with us at all times, but also at this pre-gate workshop, we got to interact with the people like this. This was amazing. of course, Arakawa and you and I were working on parameterization problems at the time. And Vikuyama had just published his successful simulation of an axisymmetric hurricane. And Dick Reed had just finished his analysis of the Western Pacific easterly waves, which he did with a triangle of stations. I remember he called it the KEP triangle. Kwajalein, Ainiwitok, and Ponape, or something like that. And he made this triangle. He did a beautiful study of that, composite easterly waves. Now, I would like to go on and talk about this paper, which I found really interesting. And this paper is by Sato and Matsuno and Miura. I'm sorry I didn't put your name on there. It was published in 2008, and it's results from their non-hydrostatic icosahedral atmospheric model. I always say NICAM. Some people say NICAM. Which is right, NICAM or NICAM? Does it matter? Yeah. So I was fascinated by this paper, and at the end, they presented the results of this aquaplanet simulation at about 3.5 kilometers, and then they interpreted the results as two worlds. So they said there was a mid-latitude world here, which is based on PV, and it's where the PV is materially conserved. So they said that the PV world is from middle to high latitudes. It's a quasi 2D vortex world, and it's governed by the conservation of PV. And then there's this other world, and I think as a catchy name, they reversed the letters and called it the VP world, which means velocity potential. And this is the world of low latitudes, convection, and waves. And this is a world where PV is not conserved because of the convection. And you can see schematically there, they have some clouds, and they have the upper branch of the Hadley circulation there. And I thought this was a really interesting world, and the interesting way to look at the world. And so the way they explained it is the mid-latitude world here is driven by radiation processes that generate a poleward gradient of temperature and therefore makes baroclinic instability. And this more equatorial world is driven by radiative processes in the long run, which change the vertical gradient of the temperature field. So some examples are in the PV world: mid-latitude cyclones, anticyclones, cold fronts and warm fronts, the polar vortex, and the mid-latitude jet stream. And in the VP world, there's the MJO, the ITZZ, the Hadley circulation, the Walker circulation, and tropical cyclones. Although in their paper, they sort of put a question mark. At least that was my interpretation. They put a question mark on tropical cyclones because they were talking about the vorticity in tropical cyclones. So here is a three-world view. So this is a slight expansion of what they proposed. And I thought, do you know that quantum physicists have a many-world view? And actually, there are so many worlds, in their view, they're not even countably infinite. So I thought, well, meteorologists ought to be able to have at least three worlds. So here's a three-world view. You have the conservative PV world, just as they described it. And then you have a non-conservative PV world. So this is a typical example of what a PV freak would do, try to expand the PV world. So you have a non-conservative PV world. So PV is not materially conserved, And actually, it can grow to very large values, like in a hurricane, 250 PV units, where in the conservative PV world, you just advect around the PV on isentropic surfaces. And if it starts off between 2 and 5 PV units, it stays there, it just rearranges. And so this, why is it a PV world if PV is not conserved? Well, the idea is that the invertibility principle for PV still holds. And so then you have the non-PV world, and examples of that would be the Kelvin waves near the equator, vertically propagating inertia gravity waves, and mountain waves. So let's see how you might justify something like this. Here's the definition of PV. It's 1 over the density, absolute vorticity dotted into the gradient of theta. By the way, this is the traditional way of defining PV, but there are other ways, and you should talk to Carrie about this, about using something besides theta there. Has made some interesting ideas about using saturation equivalent potential temperature there. But this is just the traditional PV. And note that it's a scalar because it's a dot product. So what does that mean? It only considers part of the absolute vorticity. It considers the part of absolute vorticity that's perpendicular to the theta surface. It throws away the part of absolute vorticity that's parallel to the theta surface. Now, this is weird. I'm sure students really are baffled by this. What is the unit of PV if you define it that way? It's meter squared Kelvin per kilogram per second. What the heck is that? Well, if you rearrange it, and you can rearrange it like this in the bottom box here, and you can think about the numerator here is vorticity, and the denominator is a density. Not a true density, but a pseudo-density. It's a kilogram per square meter, that's a horizontal area, per Kelvin, and Kelvin is the vertical coordinate if you're in theta. So that's a more reasonable way to write it is like that. Anyway, for inviscid adiabatic flows, PV is materially conserved, and this is true for synoptic scale mid-latitude flows above the boundary layer. Now, if you have inviscid flows, but you have diabatic heating in it, you get a term on the right-hand side which looks just like the PV, except the theta there at the end has a dot over it. So that would be your source term. So this would be more valid for tropical cyclones in the ITCZ, above the boundary layer because there's no friction in it. Now, what's in this definition of PV? There's the wind field, the vector U, and there's the mass field through rho and theta. But remember, theta is P naught over P to the kappa multiplied by the temperature, and the temperature you can write as P over rho r. So you can think of theta as being a function of rho and P. So what's in the, oh, please recognize there's an uppercase and a lowercase p here. Uppercase is PV, lowercase is pressure. So what if you have a hydrostatic balance in the motion you're talking about? Well, rho is given in terms of pressure. And what if the flow is balanced in some way? It could be geostrophic, gradient, nonlinear balance. So somehow the flow is related to the gradient of pressure. That means that everything on the right-hand side of this definition of P can be written in terms of the pressure. And so you get this box down here. The PV is L sub 2 of the pressure. L sub 2 means an elliptic operator of second order. And what that operator is, it depends on what you're dealing with, geostrophic or gradient balance or whatever. So what does that mean? It means if you know the PV, you can invert it to find the pressure. And if you get the pressure, you can get the wind and the density, and so you know the whole mass field. So this is amazing quantity, the information that's carried there in that scalar quantity. Here is an example of inverting the PV. This is a simple 2D example. So there's X along the bottom here. It's over 4,000 kilometer distance, and there's log pressure in the vertical. And the isolines on there, the solid isolines are the theta field every 4 degrees Kelvin, starting near 300 at the bottom and 374 at the top. And the PV is uniform everywhere here, outside this oval and inside the oval, but inside the oval the PV is higher. So what happens is, when you invert it, inside the oval, the PV gets partitioned to the vorticity and the stability. So the high PV means high stability and high vorticity. And the high vorticity you see by this coloring contours, and the yellows are into the page, and the blues over here are out of the page. So you have a cyclonic vorticity, and you have a high stability there. But the interesting thing is, if you go below the PV anomaly, the static stability is disrupted, and the vorticity extends below the PV anomaly. This is a typical thing when you invert an elliptic operator. The influence spreads, right? So, how does this apply to tropical cyclones? There's 3 primary questions about tropical cyclones. When's it going to form? What's its track going to be? And how intense is it going to be? And Vikuyama once described it this way. A tropical cyclone is a mesoscale power plant with a synoptic scale supporting structure. So what he meant is the inner core, where the eye wall is, order of 100 kilometers, is the power plant. And the larger scale, circulation, 1,000 kilometer scale, is the synoptic scale supporting structure. And it turns out that TC track forecasting requires accurate modeling of the synoptic scale supporting structure, and the intensity forecast requires accurate modeling of the power plant itself. That's basically why track forecasting is easier than intensity forecasting. But anyway, TCs are basically balanced PV phenomena. And the balanced wind and mass fields are invertible from the PV field. The PV is not materially conserved if we define it the traditional way with just theta. Frictional effects are confined to the boundary layer, and the evolution of the PV above the boundary layer is determined by advection and diabatic processes. Here's a result of a full physics model. It's a cross-section with radius and height, and these are isolines of PV. And this is a PV tower that formed in this model, and it has PV of about 250 PV units in it. And now, here's a famous hurricane, Patricia. It happened a few years ago, and my colleague Michael Bell tells me this is the biggest forecast bust in history. The thing was a tropical storm, and it went through category 1, 2, 3, 4, 5 in 24 hours. And no model caught this. And they were on a field program, and they almost didn't fly flights into it. But it happened in October, so they were near the end of the program, and they had these flight hours, so that they were decided they needed to use them. And they flew this thing, which was the greatest piece of luck or genius ever. And this was observed by this NASA plane. It's a B-57. It looks to me like a U-2. It has very long wings. It flies subsonically just above the tropopause. So that means it has to have big wings to do that. And you can't put any scientist on it. It's too small for that. But it has this thing underneath it, underneath the fuselage, which you can put in there, and it holds these drop zones. And these are the most amazing drop zones. They're small. They have GPS receivers on them for the winds. And you can drop these things less than 30 seconds apart. So you're flying over the hurricane, and you're dropping these things every 30 seconds. And you can really reconstruct the wind field, because the things are going through the whole troposphere, right? And so what resulted was, I think, is a best observed hurricane ever, Hurricane Patricia. And Michael Bell and his graduate student, Jonathan Martinez, they made these cross sections. This is radius here and height here. And the top one is the vorticity field, absolute vorticity field, and the static stability field is drawn with isolines here. But anyway, you can see there's a tower of very high absolute vorticity. And when you put those two fields together and make the PV field, you get this bottom diagram here. And you can see this. It's a yellow with some oranges in it. And it's up to about 240 PV units. It's amazing. And the PV structure is within 10 kilometers, right? This is 10 kilometers. And this white line here, that's the radius of maximum wind. So, could you ever produce such a structure with a toy model? So consider axisymmetric inviscid flow on an F-plane. And here is the equation for PV governed by that. So you have radial advection, U, DDR, and vertical advection, W, DDZ. And you have the PV source term there, theta dot on the right-hand side. So what if you consider a transformation of this to this, a different coordinate system here, this capital R coordinate system, which is defined by this bottom box here? Well, the right-hand side of that is the absolute angular momentum. So this is the absolute angular momentum. So that capital R, you can think of as an absolute angular momentum coordinate, but it has the units of length, right? Because the units of that term agree with the units of that term. So do a coordinate transformation from radius, height, time to potential radius, potential temperature, and time tau, where tau is equal to t. You need a new symbol tau, because partial with respect to tau is different than partial with respect to t. Can you see that? I mean, with respect to tau, you're holding the capital R and theta fixed. With respect to t, you're holding the little r, little z fixed. So tau is t, but the partials differ. Well, if you do that, that complicated equation right there, that top one, that's amazing how it simplifies. It goes to that one. That's just a coordinate transformation. Now, you can see, well, dp d tau, there's a term p times the derivative of theta dot. So there's an exponential growth built right in there, right? dp d tau is proportional to p. So what if you just divide that equation by capital P, and you get this equation here? Well, this equation on the left, it's a partial differential equation in theta and tau. It's the first order. If you look in any math book, it says, well, the way you solve an equation like that is by the method of characteristics, right? So you convert it to two equations. Well, that doesn't look like progress at all, but they're ordinary differential equations. So you have an equation for the characteristics, d theta d tau is theta dot, and then you have this equation over here, this ordinary differential equation, which tells you how the PV varies along the characteristic. So you can actually write easily analytical solutions for that. And then you get something like this. The diagram on the left is capital R on the abscissa and theta on the ordinate. And they're isolines of theta dot. It's a dimensionless version of theta dot. Anyway, just think about theta dot as maximizing in the mid-troposphere. Then if you solve this pair of ordinary differential equations that you got by the method of characteristics, you can get not only the characteristics, but the variation of PV along the characteristic. And this is isoline of the PV. It's actually P divided by some reference P, so it's dimensionless. So this isoline means 2 times the reference value, and this means 4 times the reference value. So what you're doing is you're producing a big PV in the lower troposphere and small PV in the upper troposphere. And I have 3 times here. These are dimensionless times, but watch what happens as time goes on. Remember that these isolines of PV are logarithmic, 2, 4. Now it's 16 down here, and it's 1/16 up there at the top. And then a little bit later, it's like this. It's like a PV tower, right? It's a tower of high PV, but in actual physical space, it's tilted, because this is the potential radius, and in a hurricane, the angular momentum surface tilts out with radius. So if you converted this back to little r, this whole thing would be tilted out. So that's how you can get a PV tower like in Hurricane Patricia. Now, what happens when you do that? It goes unstable, right? Because you come out here like this, and the PV is increasing, and then here the PV is decreasing. So the radial gradient of PV is opposite here and here. So it means the Rossby waves propagate in opposite directions relative to the flow, and it can go barotropically unstable. And this leads to polygonal eye walls and mesovortices and rearrangement of PV. So this has been studied with a hierarchy of models, non-divergent models all the way up to 3D non-hydrostatic full physics model. And Eric Hendricks, who now works at NCAR, he found this example. This is Hurricane Dolly, and it's just coming on the Texas coast. The Texas coast is on the left there. And it looked like it was going through this polygonal eye wall barotropic instability. This is a National Weather Service radar, and the radar is down at its lowest elevation, 1/2 degree above the horizon, sweeping around. And the blue is very low reflectivity, And the red is very high reflectivity. So this is what that kind of instability sometimes looks like in satellite pictures. Here's a close-up of that. And Jim Cawson, who's worked with Carrie on a lot of things recently, he's at the University of Wisconsin. He's actually, well, at this time he was an employee of NOAA. But he called this the starfish pattern, because he looks at this and he sees these things coming out like this, and he says there's 5 of them just like a starfish. And so that you can model that. And so now here's an interesting question. What process would produce a real confinement of the eye wall? And one possibility is that the boundary layer, the frictional boundary layer, is very involved in this. And so what if you think about this in the very simplest way? A slab model, which means there's no vertical structure in it. It's just a one layer, and it has a tangential velocity and a radial velocity, and the flow in the boundary layer is forced by the pressure field that the flow above the boundary layer is feeling. So this is a standard Ekman idea, right? When you do Ekman spiral solutions, you impose a pressure field on it. Well, here is an interesting example. This is an infamous Hurricane Hugo case, 15 September 1989. So Hurricane Hugo, think of it as being here, and the plane is down in Barbados, and they fly out there, and they're going to fly into the hurricane from southwest and northeast with that red arrow there, and they're going to fly at 1,500 feet. So while they're flying in, they're measuring the tangential wind, which is on that red curve. So they're on the inbound leg. They're in the boundary layer, only 500 meters above the ocean. And the wind is picking up, and it picks up to 85 meters a second. That's 170 knots. And it fluctuates around there. And then look at what happens in that radial interval there where the yellow is, which is around 7-kilometer radius. The tangential wind drops from 80 meters per second to 20 meters per second in about a kilometer. And Greg Holland, he said, when he was telling me about this, he said, the vorticity was 1. And I said, what do you mean the vorticity was 1? And he said, well, you usually think about the vorticity as 10 to the minus 4 seconds to the minus 1. This was 1 times seconds to the minus 1. This is 10 to the 4th higher than you usually think. And then what happened was the plane flew around in the eye, and it gained altitude, and then it left the eye on this blue curve, which is there. And you can see the blue curve, it doesn't have so much interesting stuff in it. So this wild behavior is in the boundary layer. It's not in the fluid above. And vertical velocities, if you look here at the bottom one here, the vertical velocities went up to over 20 meters a second. And then they dropped off here in the eye. And by the way, this was the end of flying the P3 in the boundary layer, because the plane, the wings flexed so much that the plane has a de-icing boot on the front of the wing, and it broke the de-icing boot. towards the end of the wing, and it was hanging down there, and they thought that if it got tangled up with the prop, it would be a disaster. And they're only 500 meters above the ocean. And the plane has a stress meter on so it measures the G-forces on the wings, and they showed it to the engineers at Lockheed, and I think they said the engineers were shocked about how high the G-forces were from this flight. So they don't fly down there anymore at 500 meters. It's too dangerous.
Wayne, go back. Let me make a remark that partly builds on something Carrie said to me after my talk. I want to quibble with your word shock. What you have is surface convergence and secondary circulation, that is the peak of that W, and extreme cyclonic vorticity. It's a front.
It's a front.
It's an axisymmetric front.
Yeah. Carrie has interpreted this in the past in terms of a front. Is that right, Carrie?
Yeah, I mean, it really has exactly the same dynamics that Jim was talking about.
Uh-huh.
You have a strong surface entropy gradient there. It's the Ekman flow is providing the background pressure, and you have this strong feedback within balanced circulation.
Uh-huh.
And it collapses these, and we used your beautiful coordinate system.
Uh-huh.
Like semi-geometry, it collapses to a front in a finite time.
Yeah. Well, let me make a counter argument to that in just a second. I don't know if it's right, but it's interesting to think about. Let me do it from this equation here. So this is the slab boundary layer model. Carrie told me once, do you know there's a model simpler than this? And I said, no. And he said, yeah, it's called the slob boundary layer model. You remember that?
Yeah, I remember.
But that model is for slobs, he said. Anyway, it has a radial equation and a tangential equation V, and it has horizontal diffusion. It has a surface drag here, the Coriolis term here, and this is a flux in and out of the slab, and then this is a radial advection here. So what you might argue, I'd be interested to hear your reaction to this, is that du dt plus u du dr is what you have in Berger's equation. And so you have an embedded, you might say, an embedded Berger's equation here. Well, to get Berger's, you have to include this diffusion in it too, right? So the radial equation has this Berger's effect, and this is the specified pressure gradient force that's coming down from above, imposed on the model. And so let me show you what you get out of this. If you take that pressure gradient, think of it in terms of gradient wind, and think about it specifying 3 gradient winds corresponding to category 1, 3, and 5 hurricanes. So this is a gradient wind as a function of R. So impose on that the pressure field associated with these. And run this model from a domain 0 to 1,000 kilometers, and do a discretization of 100 meters and a time step of 1 second. So if you take 100 meters into 1,000 kilometers, that's 10,000 grid points. And this simulation is going to run about 10,000 time steps. So why would you do it? Seems like overkill, but what happens is that the top diagram is the radial wind field, and it goes to a quasi-steady state. And so this is the steady state, and for the category 1, 3, and 5. And so you can see in the category 5, you get a radial inflow here, about 12 kilometers. And it's about a 30 meter per second radial inflow. And what happens is it comes to an abrupt stop there around 11 kilometers or something. And this is what the tangential wind field in the boundary layer looks like. So and this dashed red line is the gradient wind that's imposed. So in the boundary layer, it's this, so it's a subgradient there, but it's a supergradient there. Now, oh, and by the way, this is the vertical motion field, or the Ekman pumping that you get out of that. You can see how concentrated that Ekman pumping is. And then this is the vorticity here, and it's concentrated where the pumping is high. So let me make an argument about this. Why I don't call it a front. Because I think about the Hoskins-Brotherton model of a front, and I think about how geostrophic balance is used in that model. So what happens in that model is the flow along the front is geostrophic. And that means that this top equation is replaced by a balance between that Coriolis term there and that pressure gradient term there. So in a Hoskins-Brotherton model of a front, you don't have that. You don't have that U dUdr. Well, I know that Hoskins-Brotherton is a very idealized model of a front. And of course, true fronts do have U dUdr, but that Hoskins-Brotherton model doesn't have that. So the behavior we're seeing comes from that U dUdr, which is like a Berger's shock. And well, I know sometimes when I say shock, people say, well, it doesn't have anything to do with compressibility like a shock that an airplane forms. That's true. It's not like that. It's a more general thing about shocks as described in Whittam's book on linear and nonlinear waves. Anyway.
Just to comment, I think we can both be right. The Berger's equation in Bissett has a finite time singularity, and the Hoskins-Brotherton geostrophic approximation actually quickly flakes down in frontogenesis.
Yeah.
So, both.
Uh-huh. Yeah. Well, let me go on to this last topic here. I just have a couple minutes left. This is about ITCZs. And do you know that Alex is amazing at finding theoreticians' view of the ITCZ? He looks for the most beautiful picture out of thousands of pictures. He finds things like this. So this is a theoretician's zonally symmetric ITCZ here. And I just wanted to say that if you do that problem, you can view the ITCZ as essentially a balanced PV phenomenon. And it's zonally symmetric, like the hurricane is axisymmetric. It's inviscid above the boundary layer. And you can write the PV equation for it. And you can do coordinate transformation just analogous to like you did in the hurricane case. You can get a simplified PV equation which looks identical to what you had in the hurricane case. You can solve it by the method of characteristics, and you get things like this. Here's the ITZZ at 10 north, so latitude is on the abscissa here, and theta is in the vertical coordinate. And then here's how the PV develops in time. So this is after a brief period of time, then a little later is this, and a little later is this. So it forms a PV anomaly there, and it starts to form a tower, but it doesn't do anything like a hurricane can build a PV tower. And the ideas about barotropic instability are there. The PV gradient on a theta surface reverses signs on the two sides of the ITCZ, so you can get easterly waves off of that. Now, here's the MJO. This is weird. Here, this is a linearized primitive equation model based on Matsuno's equatorial beta plane theory. And I just want to show, here is a complete solution that comes out of this. The equator is right in the middle here. And then this is x in thousands of kilometers. So this is 8,000 kilometers. It goes the other way there. And here's the flow field. And these isolines are the geopotential anomaly. Now, in Matsuno's theory, you can break this down into three parts. First part is the Rossby wave part of it, which looks like this. Second part is the inertia gravity wave part, which looks like this, rather confined. And the third part is the Kelvin wave part of it, which looks like this. Now, do you know that if you compute the PV from this diagram, you need the wind field and the mass field to compute the PV, which you have here, right? So you can compute the PV from this, and you can compute the PV from this Rossby wave part. If you do that, you get the same PV field from there and there. So you don't get any PV from the Rossby wave part. Why is that? Well, here's just a conceptual argument.
From the Kelvin wave part.
What's that?
No PV in the Kelvin wave part.
No PV in the Kelvin wave part. Yeah. Yeah, I think I said that wrong. No PV in the Kelvin wave part. Well, here's just a shallow water argument. Here's the definition of PV in shallow water, and divide this fluid depth into a mean depth h bar plus h prime. And then the F, in the beta plane, you approximate that by beta y. And in the zeta field, remember, a Kelvin wave doesn't have any V, so there's no dV dx, there's only a du dy part to it. So the PV becomes equal to beta y plus p prime, where p prime is defined by this. It has a vorticity part and a mass field part. Now, think about the Kelvin wave. It has a maximum zonal flow right at the equator. So du dy south of that is one side, and north of that it's a different side, because u is maximum at the equator. So this du dy, it switches sign between northern hemisphere y positive and southern hemisphere y negative. And the mass field part of it, it also switches sign, not because h prime changes. H prime is the same on either side, but the beta y switches sign. So the way it turns out is that in the northern hemisphere, these two cancel. P prime is 0. And then you go to the southern hemisphere, the sign of this switches and the sign of that switches, so it still cancels. So you get 0 PV. That's a hand-waving argument, but it turns out to be true. And so the idea is Kelvin wave packets, I mean a packet of Kelvin waves, basically, it's nearly invisible on a PV map. And that word nearly, I think you have to put that there because the argument is based on beta plane theory and linearization. And it's interesting, if you do a Kelvin wave on the sphere instead of the beta plane, it has a bit of a meridional velocity to it. That's interesting. So the PV map contains practically no information about Kelvin waves. So have a friend, Brian McNulty, and he told me, Kelvin waves are the Achilles heel of PV thinking. There's a downfall of PV nerds. And I think these same arguments hold for ENSO, because ENSO has Kelvin waves in it. So anyway, PV is a useful quantity for understanding many of the atmospheric phenomena. And so I was thinking that there's sort of three worlds. There's the conservative PV world. PV is materially conserved, invertibility principle holds. There's the non-conservative PV world. PV is not materially conserved, but invertibility still is true. And that applies to hurricanes and the ITCZ and part of the MJO. And then there's this other world, the VP world, that was pointed out. So anyway, here's a thank you to Akio, and I just had a great privilege working with him on these kind of things over the years. If you want any more information about this, there's a website there. Thank you very much.
So we had some discussion during the talk, but let's take a couple more questions from the audience. And then we can take a break after that. Okay. Yes, Fred.
Thanks, Wayne. That was one of the best GFT lectures I've sat through. So my question was, generally, when does invertibility break down? In the second world you mentioned where PV is not conserved and it's still invertible. So how do you go from that world to the third world? Or what conditions do you need?
Yeah, that's a good question. You know, Kelvin waves, at least on the equatorial beta plane and linear, they have 0 PV. But they are kind of a balanced flow. It's kind of weird, isn't it? Because in a Kelvin wave, the flow is zonal, and the high pressure, the low pressure is on your left in the northern hemisphere, and it's on your right in the southern hemisphere. So the zonal flow is obeying the geostrophic relation. So in a sense, a Kelvin wave looks like it should be a balanced flow, but it has a 0 PV. So that's kind of weird. So you might think, well, invertibility is always valid if the flow is hydrostatic and if it's in geostrophic balance. But that doesn't seem to be true for the Kelvin wave.
Well, I guess you can't convert from 0.
What's that?
I mean, 0 is not invertible.
Yeah.
And Kelvin waves aren't balanced in their propagation direction.
That's true. Yes. Yes. The Coriolis force in the zonal direction is 0 because V is 0, yeah? So du dt has a term FV, but that V is 0. So, yeah, maybe that's a good way to look at it, Jim. The Kelvin wave, in one direction it looks like geostrophic balance. In the other direction it looks like a pure gravity wave. There's no Coriolis effect in it.
Dispersion relationship is a pure hydrostatic
Uh-huh.
non-dispersive.
Yes. It's not non-dispersive, right. Yeah, that's right. Uh-huh. The Kelvin wave is non-dispersive, yeah.